Hello everyone. In March of 2024, a study was published that should have given the CEOs of the big pharma companies a serious headache. Researchers had apparently found a cheap natural supplement that helped young adults shed 9% of their body weight in just 3 months, without any changes to their diet or exercise. That's about 50% more than the weight loss you get from a drug like Ozempic within the same time frame. So on one hand, you have this multi-billion-dollar search for a weight loss drug. And on the other, you have 3 researchers in a Lebanese lab with apple cider vinegar, seemingly beating pharma at its own game. Is that believable? Well, it was published in the British Medical Journal, a top-tier publication. It was peer-reviewed, so you should take it seriously, right? Well, spoiler alert, that paper was just retracted. Now, with peer reviewers obviously asleep at the wheel, it's time you got a tool to kick the tires on health news yourself. Because here's the elephant in the room that no one in medicine talks about. Even when studies aren't flawed or faked, you often won't be able to reproduce their results. The reason is a natural law that medical research almost completely ignores. It's called non-ergodicity. If that sounds cryptic, don't worry, most people haven't heard of it. It's probably because it shakes the very foundations of how we apply medical research to our own lives. So in this video, I'm going to introduce you to that law, and I'm going to give you a simple 2-step litmus test. We are going to learn how to check a study for plausibility, and then we'll answer that crucial question: will these results actually apply to me? So let's get started. Step 1, the plausibility check. Before you even think about trying an intervention from a study, you should do a basic sanity check of the data. And the first question is one that my own father asked when he saw me for the first time. Is this boy normal? Now, he was talking about my distinctly Frankenstein-shaped head at that time as a result of a forceps delivery. But in statistics, normality also refers to a shape, specifically the shape of the bell curve. The bell curve is the normal pattern we see everywhere in nature. If you measure the height, weight, or BMI, or any other biomarker of a large group of people, most of them will cluster around the average, the center. It's what we expect to see, and here is why that matters. This bell shape is a fundamental assumption for most of the statistical tests scientists use. If your data doesn't start out looking like a bell curve, the conclusions will be built on shaky ground, and they are likely to collapse. So a weirdly shaped distribution at the start of a study is a major red flag. Now the problem? Papers almost never show you this shape. They just give you the summary numbers, the mean, the standard deviation, and the sample size. But we can use those numbers to reverse engineer what the group of participants actually looked like. And this is where a tool called Sprite comes in. Think of it as a data forensics tool that takes the summary stats and gives us a kind of a police sketch of the crowd. So let's be data detectives. Let's look at the apple cider vinegar study. The authors told us the mean age, the standard deviation, and the range of participants from 12 to 25 years old. And when we ask a tool like Sprite to show us what a group of people must look like to have those exact numbers, this is what we see. As you can see, that is not a bell curve. It's what we call a bimodal distribution. It has 2 peaks on either extreme, not just one in the center. And that means the participants were clustered at the extreme ends of the age range. A big group of 12-year-olds and another big group of 24, 25 years olds, with almost no one in the middle. And this brings us to one golden rule of averages. Don't average apples and watermelons. An average is only meaningful when you average similar things. An average weight of an apple and a watermelon, for example, is a useless, misleading number. And that bimodal distribution of that study tells us the researchers were mixing two different types of fruits, young adolescents and young adults. And because their starting sample was so flawed, the ground for their statistics analysis is more than shaky. We can't trust their conclusions. Okay, so let's say a study passes the plausibility check. We then can move on to step 2 of our credibility check, the translatability check. It basically asks and answers the question, will it work for me? And this is where we need to understand ergodicity. So let me explain it with a tale of gambling. Imagine a roulette strategy where on any given day, 99 out of 100 gamblers walk away 50% richer. But one person, 1%, goes completely bust. The group average looks fantastic. You have a 99% chance of winning big. That's the cross-sectional view at any one day. But now let's look at any one gambler over 100 days. His chance of eventually going bust is 100%. The amazing group average is a terrible predictor for the individual over time. This system is non-ergodic. Now here's scenario 2. Different game, different rules. Instead of 1% of gamblers going bust on any one day, 1/3 end the day up 20%, 1/3 ended with exactly where they started, 0% change, and 1/3 end up with a loss of 10%. The average result across all 100 gamblers is a gain of, on average, 10%. This is the cross-sectional perspective. In this configuration, for any single gambler over 100 days, the results will be pretty much the same. He will have some great days with plus 20%, some flat days with 0%, and some losing days where he loses 10%. And over time, his personal average return will also converge to around plus 10%. In this case, the cross-sectional average, plus 10% for the group, is a reliable predictor of the longitudinal average, again plus 10%, for any given individual. Systems like that are called ergodic. The problem? Mother Nature, and especially human biology, doesn't do ergodic very well. We are complex, non-ergodic systems, and this is why you can't just blindly translate a study result to yourself. So what can you do? You reframe the question. Instead of asking, will it work for me? You ask, what are my chances of even recognizing the effect? A real study signal of a 6-point drop in blood pressure, for example, can get completely lost in your body's natural noise. A massive study found, for example, that the average person's blood pressure naturally fluctuates by about 10 points between doctor's visits. And that's a lot of noise. The only way to know if a signal is real for you is to first measure your personal noise level. And this is where you become the scientist. By monitoring your blood pressure daily for 2 to 3 weeks, for example, you can establish your personal baseline mean and your personal standard deviation, which is your noise level. And once you know your noise level, you can calculate the minimum signal you need to see for it to be real, statistically significant. How to do that in practice is the subject of my full-length article on Substack and Medium. So what's our conclusion? Your own data is the only gospel. This N of 1 method, turning yourself into a clinical trial of 1, is the only way of knowing for sure if a study's results apply to you. No guru, no headline, not even a prestigious medical journal can tell you what will work for your unique body. So get used to the idea of doing your own checks. First, check for plausibility. Is the study built on a solid foundation? Then check for translatability. Is the signal big enough for you to detect? And finally, run your own experiment. How to do that is the subject of my full-length article, which also gives you access to downloadable tools that help you run these two checks. So I hope these tools help you get started on that journey. Thanks for watching and see you again soon.